Okay, let's work through problem 1 from the final exam. So the spacecraft in the movie 2001, A Space Odyssey, has a rotating cylinder to create the illusion of gravity, and inside this cylinder the crew can walk and exercise, feeling as if there's something, some force of gravity holding each crew member down to the surface. Okay, so part A of the question asks, if the cylinder radius is about 3 times a crew member's height, what should the rate of revolution of the cylinder be in order to replicate Earth's gravity? So let's draw a circular cylinder. So draw it in cross-section here. Here's the center of the cylinder, and the center of the cylinder, we'll call the radius of the cylinder capital R. And now we'll draw a vertical line here, and we'll go 1/3 down, and here is the height of a crew member. Okay, so here is H, and about 3 times H is the radius. Okay, and now we want gravity to act on the center of mass of the person. So the center of mass of the person is here, and so that is probably about 2.5 H, right? So we go up half an H. Here we start at the center, we go down 3H, and we go up half H, and we get 2.5 H. And now, so we'll say H is about 2 meters, which is a nice round number for the height of a person. And now we want to say, how do we replicate the acceleration of gravity, right? So an object at the Earth's surface, near the Earth's surface, in free fall experiences an acceleration g. Now, instead, we want a centripetal acceleration to simulate the Earth's gravitational acceleration. So we'll have A equals omega squared r, and this R is going to be acting at the person's center of mass, so that's omega squared times 2.5 H, and this should equal G, right? Because the acceleration should equal G. So instead of having force of gravity equals mg, instead we'll have the centripetal force equal to m omega squared r. Okay, so now we have omega squared times 2.5 times 2 meters equals g, which is 9, well here it equals g, which equals 9.8 meters per second squared. So now we have omega squared equals 9.8 meters per second squared divided by, so 2.5 times 2 meters is 5 meters. 5 meters. Okay, so then, actually to make this omega, we'll take the square root here on both sides. And 9.8 is pretty close to 10, so basically omega is going to be pretty close to the square root of 2. So this is about 1.4 radians per second. Or to put it into rate of revolution, we'll have the frequency, which is omega over 2 pi equals, so this is 1.4 radians per second divided by 6.28, which is 0.22 hertz, or 0.22 revolutions per second. Okay, so it has to go around once about every 4 or 5 seconds in order to simulate the Earth's gravity if its radius is about 3 times the height of a person. Now the second part of the question asks, how much, for a person standing in this cylinder, how much do the gravitational acceleration at the top of her head and the gravitational acceleration at her feet differ. Of course, on Earth they would be the same, but because we're simulating gravity with rotation, we'll see that they differ. So we have the acceleration at her feet is omega squared times the radius at her feet, which is, so omega is 1.4 per second. So that's omega squared times 6 meters. Whoops. Omega squared times 6 meters, which is 11.8 meters per second squared, and then the acceleration at her head is omega squared times the radius at her head, in other words, the distance from the center of the cylinder to her head, which is, okay, omega is again 1.4 radians per second, so we square that, and then we multiply by 4 meters, which is the distance from the center of the cylinder to the top of her head, if she's 2 meters tall, and we get 7.8 meters per second squared. So now we have a feet minus a head equals 4 meters per second squared, or if you like, a feet divided by a head equals 3/2. So in other words, gravity is 1.5 times, the simulated gravity is 1.5 times as strong at her feet as at her head, and you can see that this number 11.8 at her feet is a little bit larger than the 9.8 meters per second squared you feel on Earth, so her feet will feel a little heavy when she picks them up. And you see that the 7.8 at her head is a little bit smaller than the 9.8 you feel on Earth, so she might feel a little bit lightheaded. But on average, this works reasonably well to simulate the Earth's gravity. And if you could make the cylinder bigger, say 10 times a person's height, then I think it would be even more natural feeling. Okay, so that's problem number 1.